Hello everyone. Today we'll talk about the solution to the problem prime subtraction operation. This problem has two parts. The second, more important part, is this abstract problem where we're given an array and we also have some set of possible values. We can, from any element in our array, either don't do anything or subtract some value from this set from that element. The same value from the set can be used for multiple elements. However, for every element we can subtract at most a single value from the set. And you want to make that array strictly increasing after performing some, maybe zero operations. And the difference from that abstract problem and our problem here is that we are being told that what we can subtract from a value is any prime that is strictly smaller than the original value in that spot. So in essence, we can just generate all the prime numbers that are up to the maximum value in our array. So we just can calculate the maximum value. Those are the possible values that we can subtract. So these are the values in the set. And we have to make sure that if the value that we want to subtract is greater than or equal to the current value, that means the prime is not strictly smaller. And we can, since the approach that we'll be taking will be a greedy approach, we can at this point just say that it's impossible to generate that array. But I'm getting ahead of myself. How do we solve this abstract problem? Well, an easy way of seeing why a greedy strategy works is to, for instance, start from the back. The last element, should we ever decrease it by anything? Well, we shouldn't decrease it. Maybe it's possible to make the array strictly increasing by decreasing the last element, but even if it's possible, it'll be even better for us not to decrease it. We want this element to be as big as possible. The next element, it has to be smaller than this one. If it's smaller already, we shouldn't do anything, we shouldn't make it even smaller. If it's bigger, we have to decrease it so that it becomes smaller. But again, should we decrease it by a lot or as little as possible? Well, it's better to decrease it by as little as possible. That's because any solution that will work for us decreasing this element too much, so let's say that this is the last element in the array, we can choose to decrease the next to last element either to be something like this or something like this. Then if there is a solution that creates an increasing array that works with this smaller value, then it'll still work with the larger value. But this is not true if the prefix would be something like this. Then it would not work when we reduce this value to be too small, but it will still work with us reducing this value by a little bit. So at any point we want to, and of course this inductively works for the next element, and so on. So you want to go in from the right, decrease the element only as much as we need to decrease it so that it becomes smaller than the subsequent element. Okay, so let's see the code, and the code will start with a sieve that generates all the prime numbers which we can later use for subtraction. The idea of a sieve is very simple. It's based on an observation that, first of all, if we have some number, let's say 3, then all the multiples of that number are definitely not prime, because they are integer multiples of 3. So by starting at the number and crossing out all the multiples of that number as not prime, we can get rid of some composite numbers easily. And more so, if we have a number like 11, and we go to 11, going through all the previous numbers first, we see that 11 is not crossed out. That tells us that this value is prime. Because if there is a value and that value is not prime, that means that it's a multiplication of some two smaller integers that are bigger than 1. So it will have been crossed out when going through those smaller numbers, right? So for instance, we know that 12 is 2 times 3 times 2 again. It also divides by 4, it divides by 6. So for any of those numbers, when crossing out their multiples, we will have crossed out the number 12. The way I implement the sieve is that I also remember the number which crossed out the value. It's not necessary in this problem, but it's useful in other problems because that allows us to quickly factor numbers, because we remember at least one of their divisors. So the sieve will be implemented like so. At first, every number has itself as the value in the array. So we have 1, 2, 3, 0, 1, 2, 3, 4, and so on. We're only interested in values from 2 up, because only those values can be composite or prime. So we start from 2. And now, if we know that the value in the array is smaller than the current index, that means that this number is composite. We have already crossed it out, at least when going through the value divs of I, so we don't have to do anything. Otherwise the number is prime, so we should cross out its multiples, so we will just iterate starting from 2 times the value and going 3 times, 4 times and so on, so it will just be a range from I plus I to max v plus 1, which is our top of our end of the interval, increasing the value by I at every step. And we'll write I at the position of the number j, which is equivalent to crossing out. So for instance, if I was equal to 3, then we'll start with 6, then 9, then 12, and so on. This is the example that I've shown before. At the end, in the array divs, only the values that are 2 or more, and whose value at their position in the array is equal to that position, are prime. And now we can solve our problem. We'll be looking at values starting from the next to last, so from the n minus second down to 0, step by step. If the value is smaller than the next value, then we don't have to do anything. That's what we mentioned before. We don't want to decrease a value that doesn't need decreasing. Otherwise, the value needs to be decreased. It needs to be decreased at least by the difference between it and the next value, and also one more step, because we want the array to be strictly increasing. So in other words, if we have value 6 here and we have value 8 here, then the least that we can do is to get the sequence 5, 6, we have to decrease it by 3, which is 8 minus 6 plus 1. And we want to make sure that that difference is a prime number. This is this condition. So it has to be at least equal to 2, and at least equal to that difference, plus 1. And now, if it's not prime, we want to make that difference bigger and bigger until we reach a prime. So, for instance, if we land at 6, then you want to check if 7 is prime, and yeah, 7 is prime, so we're happy to use a 7. And we're just doing it step by step. We could pre-calculate something like the next prime number from every value, but it's not necessary here to pass the problem's tests or to fit in the constraints. And of course, we have to make sure that the difference doesn't exceed the value of the current number, because in that case we also make sure that we don't run out of the array, because that array ends at max value plus 1. And of course, here is that check if the prime number that we want to subtract is too big, because it might be that we have value 7 already, we have to subtract 6 from it. 6 is not possible, so we have to subtract 7, but 7 is also not possible because it has to be strictly less than. So in that case, we just return false. Otherwise, we perform our modification in place. So in the next step, we'll be looking at the value to the left of the ith value. So we'll be seeing the modified value at position I. And of course, after this for, if we never returned false, we just return true. And the value of nums after running this algorithm is that proof of concept that indeed it's possible to make that array strictly increasing by only performing operations as told in the statement.